All right, everybody, we are starting chapter 3, part 2 PowerPoint now. This section should be pretty short, so I'll do a couple of videos. But essentially what we're doing, we've learned all the calculation stuff that we need for doing mole calculations and everything in chapter 3. But now we need to get a little bit better at writing reactions. Again, a lot of times problems are going to start out where they give you some information, you have to write a reaction from that, and then you have to start your calculations, okay? So a couple of things. One is you need to practice writing these reactions so you can get all the formulas correct and balanced equations and all that. But the other thing you need to do is work on speed. You got to be able to get this stuff down quickly, be sure of yourself, and the only way that happens is with practicing more problems, okay? So, basically, if you are starting to get frustrated, overwhelmed, don't give up. We'll make it. I mean, there's plenty of materials to help. If you will email me and check with me, I'll do what I can to help you get through. Now, there are 5 big types of reactions that we're going to learn in this section. I will say that this material crosses over between chapter 3 and chapter 4. The book, a couple of editions ago, they kind of changed the way they group things. It used to be that they introduced all the reactions together. Now, I think early in chapter 3, they introduced like combination and decomposition reactions. And then when you get to chapter 4, you get to see the single replacement and double displacement reactions. I'm not even sure where combustion fits in. But I do kind of like this slide. It's actually a good example of how a lot of the reactions go. The top one, synthesis, it also has 2 other names depending on what book you're using. Synthesis reactions can also be called combination reactions, and they can be called addition reactions. The idea is you're taking 2 things, putting them together to make one thing, kind of like the circle and the smiley face. You put them together to make a normal smiley face. Anyway, so each of those, if you look at them, they actually are very representative of what's going on in each of the reaction types that we're going to learn. There's one type that's not on here because it doesn't really fit with the schematic. That's going to be reduction oxidation reactions, which are called redox reactions. That'll be the last one that we do. They're kind of weird, but it's an important concept if you want to understand how reactions are actually occurring. So we'll cover that when we get to it. But we're going to go one at a time. Essentially, we're going to go combustion first. So basically, it's one that most people are already kind of familiar with. If you take a sample and burn it, and if whatever you're burning, we call that the fuel. We're burning it with oxygen from the air. If you don't have both of those present, then the reaction doesn't work, okay? So we have to have a fuel and oxygen together to get a chemical reaction. So if we are, a lot of times students learn, somewhere they pick it up, I'm not sure it's the book or just because most of the examples, we tend to burn things that are hydrocarbons, whether we're burning a piece of wood or gasoline or propane or natural gas or any of those different things. They tend to be hydrocarbons, and when you burn hydrocarbons, you get the same products every time, which are carbon dioxide and water. And so sometimes students think, okay, when I do combustion, I always get CO2 and water. That's too much of an assumption. It takes you too far, and it's going to mess you up sometimes. You technically, when you burn something, you're going to make the oxide of whatever elements are in the fuel, okay? So if you're burning a fuel that has carbon and hydrogen in it, well, when you burn carbon, it's going to make CO2. When you burn hydrogen, it's going to make water. So if your fuel is made up of carbon and hydrogen, then yes, you're going to get CO2 and water as your products. But we can burn other things. In lab, later on, we're going to burn magnesium. If you burn a piece of magnesium in air, well, magnesium reacts with oxygen, and it cannot form CO2 and water. There's no carbon, there's no hydrogen in the fuel. If you burn magnesium and oxygen, you're going to make the oxide of magnesium, which will be MgO. Magnesium is +2, oxygen is -2. So you got to put the charges together the right way. But so my point there is, while we often will develop a habit where it seems like combustion always involves a hydrocarbon, that is not always true. And since we burn a hydrocarbon that gives us CO2 and water, we get used to those always being in the products. Well, that's not always going to be true either. Okay. And then last thing about that, most combustion reactions are fast. Most combustion reactions are going to involve a flame or some kind of active burning or whatever. But we also have slow combustion reactions that can occur. Like if you take a piece of iron, like an iron nail, and just leave it outside on the ground, and it rains and gets just kind of sits there and starts to rust and all that kind of stuff. The rusting of iron, that's actually the reaction of iron with oxygen from the air to form iron oxide. That is a combustion reaction. It's slow, there's no flame involved, but it's still combustion. Okay, so just realize this category is broader than most people think it is. Because anytime you react a element or compound with oxygen and you form the oxide of the elements that are in the fuel, it's always combustion, but the way it can appear to you can be very different depending on what it is you're burning. Okay, so from that we should be able to write a balanced equation for the combustion of, if my fuel is ethanol, I should be able to write a reaction. Now our keys, when we do this, we're always going to have the fuel, we're always going to add oxygen as oxygen gas, so that's going to be O2, and then we're going to make the oxide of the elements in our fuel. So I'm going to pull my screen over. Now if I use so I've got C2H6O is my fuel. Ethanol is a liquid. I'm going to burn it with oxygen gas. And then when I burn it, I'm going to make the oxide of the elements in my fuel. So I'm going to make the oxide of carbon, which is going to be CO2. And CO2 is a gas. And I'm going to make the oxide of hydrogen, which is water. Now, a little variation here. Water, there's two different ways you can do this. I learned when I was a student that you always put the normal physical state of every substance at room temperature when you write a reaction. So I learned that you should put liquid beside water pretty much always, unless it tells you that you're doing it a certain way. Okay? Now, that's how I would expect it. But your textbook does it a different way, and then Mastering Chemistry is our homework system. It's inconsistent. Sometimes it does it one way, sometimes it does it the other way. So the second way you could do it is saying, when I burn a fuel, it's going to give off a flame, like it'll be a flame, there'll be a lot of heat coming out because combustion reactions are always exothermic. So when the water is formed, it's going to be really hot and it's going to come off as steam. Okay, so the book and Mastering Chemistry might put gas by water. I might put liquid. I don't care which way you go, you just have to pick one. Okay, so I'm just going to put liquid because that's what I normally do. But like I said, if you're in Mastering Chemistry and you try to, it's going to make you type in reactions into the homework problem. If it counts it wrong and you can't figure out what else is going on, think about the physical states and make sure that for water, sometimes it's going to want it to be gas, sometimes it's going to want to be a liquid. I wish it was more consistent, but it's not. It kind of goes back and forth. Okay, so then I should balance my equation. So when I start out, I'm going to have 2 carbons over there, so I'm going to put a 2 in front of CO2. Got 6 hydrogens over there, so I'm going to put a 3 in front of water. That now gives me 4 oxygens here plus 3 here. That's a total of 7 oxygens on this side. I've got 1 in my ethanol, so I need 6 more right here, so I'm going to put a 3 in front of O2. That gives me 7 oxygens on each side of the reaction. Okay, now let's do one more combustion reaction. If I'm on July 4th and I get a sparkler and light a sparkler, the way a sparkler works is actually it's little chips of magnesium, and when you light it up, you're burning pieces of magnesium. Okay, so the reaction, I'm burning magnesium in the air. So magnesium is a solid. Oxygen is a gas again. Put them together. This time when I do it, I make the oxide of magnesium, but whenever I put them together, magnesium and oxygen, that's a metal and a non-metal. Anytime in a reaction that you're forming an ionic compound, you have to think about their charges and make sure you put them together in the right ratio. Okay? I can't just look over here and say there's one magnesium and two oxygens. I can't just carry that over and try to do that because that might not be the right ratio for these two elements. All right? So magnesium is in group 2. I know it's +2. Oxygen is in group 6. I know it's -2. So +2, -2, that is the right ratio. Ionic compounds are going to be solid if there's no water present. And in this reaction, there's no sign of water, so I'm going to put solid there. Finally, I have to balance the equation. 2 oxygens there, so I put a 2 here. 2 magnesiums here, so I put a 2 there. And that is a balanced equation. These are both combustion reactions, although they look different. Like I said, many combustion reactions form CO2 and water, but don't get trapped by thinking that it's always going to be the exact same. All right, so now back to our PowerPoint. So our next type of reaction is called single displacement. The idea is we're going to have a compound. Usually they'll contain 2 elements most of the time. We're going to add another element to that compound, and the new element that we've added is going to replace one of the elements that was already present. Okay, so the general form of it looks something like this. I add element A to compound BC. A wants to jump in and kick out either B or C. Okay, now the way it works, a example is not exactly as politically correct as it maybe once was. If a couple is dancing on a dance floor, and we'll assume it's a boy and a girl dancing on the dance floor, another person walks up and wants to cut in. Okay, most of the time, if a boy walks up and wants to cut in, he's going to try to take the place of the other boy. We're just going by percentages here. So, and instead of boys and girls, when we talk about a chemical reaction, we're going to think about positive charge, negative charge. If A is a metal and wants to have a positive charge, when I look at BC, I should know, and this is something I haven't mentioned up till now, but with BC, we always write an ionic compound metal first. It's always the positive ion first and then the negative ion. Okay? So the positive ion always leads when you write an ionic compound. So if A is a metal and wants to be positive, B is a metal and is positive, then A is going to take the place of B. So A jumps in, kicks B out. So then in my product I have AC and then I have B. Now, a trick here, when we form AC, that is a new ionic compound I formed there. I have to think about the charges because A and B are both metals, but A might be a +2 metal, B might be a +1 metal. So when I go from BC to AC, they may not actually have the same ratio between B and C versus A and C. So you always have to just look at the charges, make sure you're putting each set together in the right ratio. Okay, an example of that, copper and silver. So I have silver nitrate, and now this time BC is actually, it's an ionic compound where the C part is nitrate, so it's a polyatomic ion. But it's still basically 2 things. There's the silver ion and there's the nitrate ion. Okay, positive, negative. They're floating around in a solution. So again, it's like a couple dancing on the dance floor. And then all of a sudden, you drop in an outsider. So copper comes into the solution from the outside. He's a solid. He wants to dissolve into the solution. He wants to join the dance. But he can't do that unless he has a partner. So what happens is the copper has to come in and kick somebody out here. Well, copper's a metal. He's going to kick out the other metal. So copper jumps in, silver gets kicked out. To write the products, silver got kicked out, so that's why silver is by itself. Copper is now with nitrate. There's my copper nitrate. Okay? Now, copper can form, actually, copper has 2 different charges. Sometimes copper is +1, sometimes copper is +2. there's no way for you guys to know which one's going to be more likely or whatever. That's just above the level that I expect for you to know. So I would probably tell you in this case, if this reaction happened, copper is going to form the +2 charge state. So I would kind of help you out with that. But then you have to know if copper's +2, which I would tell you, nitrate you have to memorize is -1. So when I put them together, even though silver and nitrate were 1-to-1, that was because it was +1 -1. When I form my new compound, now it's +2 -1. So the 2 comes down, the 1 goes down, so that ends up being my formula for this compound, and then silver got kicked out. Another thing that I haven't mentioned before, when you write your products, it doesn't matter what order they're in. Sometimes you'll put silver first, and then this is my second product. You could also switch them, okay? As long as you have the correct 2 products, both of them on the right side of the equation, you're good to go. Same thing on the reactants. It doesn't matter if you say copper plus silver nitrate, or you can say silver nitrate plus copper. The order of the reactants, the order of the products doesn't matter as long as you have the formulas correct, okay? Now, our issue, PowerPoint pointed out, we got everything right, but we forgot to balance the equation. There's actually, if I had the speakers on, there's a noise. I think it's Homer Simpson saying dope when I do that. So then if we balance the equation, because there's 2 nitrates there, we have to put a 2 there and a 2 there. That ends up being the proper equation. So now it's balanced, and I think there's actually an applause in the sound if you turn that on. Now, when we look at those reactions, there is a section in chapter 4 that expands on this topic called the activity series. And again, we're going to talk about it in lab, and you're going to read about it, but make sure you take a look. I got to stop the video before it gets too big to upload.